Bienvenidos al octavo día de exposiciones que organiza el Consejo de Aeronáutica y el Espacio del Colegio de Ingenieros. Y hoy día esta breve introducción la hago en español para luego hacer un cambio al inglés, porque hoy día tenemos un expositor que nos honra con su presencia y directamente de la Universidad de Harvard. Por lo tanto, ahora hago la presentación en el idioma para que nos podamos entender todos. Good morning, everybody, distinguished audience, ladies and gentlemen. I'm Eduardo Guevara from College of Engineers of Chile, and it is my great pleasure to welcome you to the 8th day of this month's celebration of aeronautics and space, sponsored by the Aeronautics and Space Council, the Chilean Space Association Chile, Universidad Técnica Federico Santa Maria, and other collaborators like Chilean Air Force and universities. Today's presentation has something different than yesterday's, when we were introduced to the UFO or UAP today theme, occasion that made me think an event that happened in the year 1999. During a break at the Air War Academy around 10:00 a.m., when I left the room towards the patio, and I saw 4 comrades looking at the sky, and I asked them, "What are you seeing?" One of them very seriously told me, "UFOs." I laughed slightly. "Yes," he said, "seriously. Look up at 11 o'clock. There are 3 objects, and they are evolving at high altitude." Many times you need evidence to believe or accept something like this. That experience forever marked my interest in UFOs or UAPs. This event gave me undeniable proof that apparently we are not alone in this universe. Of course, with this evidence come many questions, like where they come from, what kind of technological advances do they have, what is their society like, why don't we put more effort in scanning the sky or space? Today's speaker is related to this topic, but in a broader way. He has written many books referring to the need to search in the space of our solar system and beyond this for evidence of other civilizations. His perseverance is an example because when this subject is talked about, there are many scientists and people who don't even wait to discuss the possibility of other civilizations existing. Today, we have, who is the head of the Galileo project, founding director of Harvard University's Black Hole Initiative, director of the Institute for Theory and Computation at Harvard Smithsonian Center for Astrophysics, and the former chair of the Astronomy Department for Harvard University between 2011 and 2020. He chairs the advisory board for the Breakthrough Starshot project, and he is a former member of the President's Council of Advisors on Science and Technology, and a former chair of the Board on Physics and Astronomy of the National Academies. He's the best-selling author of Extraterrestrial, the First Sign of Intelligent Life Beyond Earth, and a co-author of the textbook Life in the Cosmos, both published in 2021. His new book, titled Interstellar, was published in August 2023. So it is an honor for us to receive Professor Abraham Lev on our platform, who will talk about the new frontier of interstellar objects. Please, Professor Lev.
Thank you so much, Eduardo. It's a great privilege to speak with you. And I visited Chile just a decade ago and enjoyed it very much. We have a lot of facilities in Chile that observe the universe at large. So let me share my screen and I'll make a presentation. And then hopefully we'll have a lot of time for questions from the audience. So just a few weeks ago, I published the book Interstellar, which you see here, and it discusses the consequences of finding an object that came from outside the solar system near Earth. You can think of it as finding a package near your mailbox, or finding a tennis ball that was thrown by a neighbor among the rocks that you are usually familiar with in your backyard. That has great consequences for the future of humanity, as I'll describe. And this is a new frontier that started only over the past decade. The first objects from outside the solar system were found over the past. Excuse me?
Sorry, Professor, there is some problem with the screen. We are not seeing your slide.
Oh, okay. I shared my screen. Let me see here. Let me do it again.
Okay.
Can you still not see my slides?
Yeah, cannot be seen.
Okay, so now let's solve this problem, because it gives me a whiteboard from the Zoom for some reason. It doesn't allow me to share my screen.
Okay.
If you can make me a co-host, I think it would work.
Okay, Constanza?
I'm already doing this.
Sí, si lo puedes dejar como
Oh, okay.
co-host.
Let me try now. Let me see if that would work. No? Can you see my screen?
Yes, absolutely.
Okay, so so let's start again. This is the cover of my book, Interstellar, that just came out last month and discusses the implications of finding a package in our backyard from another civilization. And the reason I'm discussing it is because we launched 5 probes to interstellar space. The first was Voyager, and it's making its way out of the solar system. And we know that most stars formed billions of years before the sun. So if there was another civilization like ours that started earlier, it takes less than 1 billion years to traverse the entire Milky Way galaxy with a probe like Voyager. So we could potentially find such probes in our backyard because they started the journey a long time ago. And it would save us the need of going out and visiting our neighbors if we can find evidence that they exist right next to us. And so this frontier of interstellar objects started over the past decade. It is the search for technological needles in a haystack of rocks, because within the solar system, the objects we had seen so far that are bound to the sun are rocks. And we found 3 interstellar objects over the past decade. The first one on January 8th, 2014. It was a meteor, roughly 0.5 meter in size, the size of a watermelon, that collided with Earth. And what was unusual about it is it moved very fast, faster than 95% of the stars near the sun. And also it disintegrated only at very high stress. It had material strength larger than all the space rocks that NASA cataloged over the past decade, 272 of them. And the composition of this object was very different than solar system rocks. The second object from interstellar space was discovered by a survey telescope in Hawaii. It was given the name Oumuamua, which means a scout in the Hawaiian language. It's roughly the size of a football field, 100 meters. And it was anomalous in being flat, like a pancake in its shape, based on the reflection of sunlight as it was tumbling every 8 hours. And also it exhibited a non-gravitational acceleration, a push away from the sun without any rocket effect from evaporation, like comets show. And moreover, it originated from the local frame of the Milky Way galaxy. Only 1 in 500 stars is so much at rest as Oumuamua was in that frame. And finally, in August 29th, 2019, a comet from interstellar space was discovered by an amateur astronomer, Gennady Borisov. It was hundreds of meters in size, and it looked just like the comets that we are familiar with. So altogether, out of these three objects, the first two appeared unlike the familiar rocks in the solar system. They looked anomalous in different ways. Could they be technological in origin? That's what intrigued me. Now, what is an interstellar object? Just imagine the sun here drawn in red. It has a certain amount of mass in it and gravity associated with it. And if you imagine an object moving relative to the sun faster than the Earth is by about 42 kilometers per second, where the Earth moves around the sun at 30 kilometers per second, then this object will not be bound to the sun by gravity. So we are familiar with all the objects in the solar system that are bound to the sun, like the planets, including the Earth, or asteroids or comets. But here we are talking about objects that are moving too fast to be bound to the sun. And as I mentioned, three of them were discovered over the past decade. The first two appear to be anomalous. Oumuamua was the first one reported, and it was very puzzling as to what is pushing it away from the sun. I suggested it's just the reflection of sunlight. And for that to be effective, the object had to be very thin, like a sail. And nature doesn't make thin objects like that. So I suggested maybe it was produced technologically. Maybe it's the surface layer of a bigger object that was torn apart. And a few weeks ago, there was a play that was shown at my home called The Piece of Sky, inspired by my work on Oumuamua. The hope is that this play will present in New York City within a year. And let me just mention a few excerpts from the content of this play. One of the questions that being raised in the play is the following, and that relates to the academic community. It relates also to social media. Why is childlike bullying more prevalent than childlike curiosity? After all, curiosity should drive science. But whenever something different is being proposed, there is a pushback, and that suppresses innovation in science. Another thing mentioned in the play is I mentioned that my mother told me when I was born at the nursery, all the other infants were looking at things in their cribs, but I was looking at the ceiling. I have to break out from that habit entirely. It gets me into trouble. And finally, my advice to young scientists is never to pretend to be the adult in the room. Maintain your childhood curiosity. So based on this advice, I established the Galileo project, which is focused on studying objects near Earth that came from outside the solar system. And the project was established more than 2 years ago. And by now, we have an observatory that is functioning at Harvard University, monitoring the entire sky at all times. And let me show you a short video that describes the instruments being used.
Welcome to an overview of the Galileo project's development site, codenamed Pigeon Run. Our instrumentation suite consists of both wide field and narrow field sensors. Wide field sensors are used for target selection and tracking, while narrow field sensors gather higher resolution data on potentially anomalous objects. Our main instrument is DALEC. a hemispherical array of 8 infrared cameras. Next to it is the Alcor, a secondary high-resolution optical all-sky camera. Together, these instruments continuously monitor and track objects in the sky, analyzing them in real time for potential anomalous activity. This is AMOS, our acoustic monitoring omnidirectional system designed to detect and record acoustic signatures across the infrasonic, audible, and ultrasonic bands. AMOS also houses an ADS-B antenna for logging aircraft transponder data, allowing us to quickly separate known from unknown objects. Here we have Skywatch, a multi-static passive radar system designed to detect and track multiple objects simultaneously, measuring object positions and kinematics. And Pac-Man is an environmental monitoring system for measuring local weather conditions. Sensors include an anemometer, temperature and pressure sensors, a particle counter, and a flux gate magnetometer. Next up is Spectre, a radio spectrum analyzer with a wide band antenna for measuring radio and microwave emissions. Beacon is currently our only narrow field instrument. Beacon is a high-resolution pan-tilt zoom camera capable of 40 times optical zoom. Our instruments collect a wide range of data, all of which is fed to our computing enclosure housed beneath the DALEC and Alcor instruments. Here, data is processed and analyzed in real time. Objects detected and tracked by the wide field instruments are localized in 3D space and analyzed for unusual characteristics. Selected targets are then sent to the Beacon PTZ for follow-up observation. Finally, data is recorded to disk and uploaded to the cloud via Starlink. These combined systems comprise the current version of the observatory class system, with many refinements, additions, and upgrades scheduled for near-term implementation at Pigeon Run.
So this was a brief summary of the system that we have. And we are planning to expand it in the coming months and figure out distances of objects in the sky by using multiple cameras at different locations. We're also planning to make copies of this system and place them in various locations within the US so that we can get better statistics of unidentified anomalous phenomena that the US government is unable to figure out. And we also use satellite data from Planet Labs, looking at objects from above, not just from below. So we have a lot of work to be done in different phases. The number of copies that we make of this observatory will depend on how much funding we have. Each of them is a fraction of $1 million in cost. And we have published 8 papers describing the instruments that we are using. Now, what I will talk about most of my presentation today is the interstellar meteor that I mentioned. So that was observed almost a decade ago, and based on its unusual properties, I decided to lead an expedition to the Pacific Ocean to collect materials left over from the explosion. And I wrote 43 diary reports on medium.com, which you can find. There were millions of people around the world who read them during the expedition. They were translated to Spanish. The story started with a detection back in 2014, and we wrote a paper saying, here is the first interstellar meteor ever discovered. And then my colleagues argued that they don't believe the data from the US government. And so it took 3 years until the US Space Command wrote the letter that you see on the left here and sent it to NASA, confirming at the 99.999% confidence that indeed this meteor came from outside the solar system based on its high speed. So in a way, the Department of Defense came to my defense. And our paper with my student Amir Siraj was accepted for publication. And then I decided to lead an expedition to study the materials left over from this meteor. And the reason I did that is because the government also released the light curve of the fireball that was generated as this meteor exploded as a result of its friction with air in the lower atmosphere, about 20 kilometers over the Pacific Ocean. And there were 3 flares separated by 1/10 of a second from each other. And based on the fact that the object disintegrated only in the lower atmosphere, we were able to conclude that it had material strength tougher than all the space rocks cataloged by NASA over the past decade, 272 of them. So it was an outlier in material strength, tougher than even iron meteorites. And that raised the possibility that perhaps it's a Voyager-like meteor. Imagine our own Voyager colliding with another planet in the future that looks like the Earth. It would appear as a meteor of unusual material strength and unusual speed. And indeed, this meteor was moving faster than 95% of the stars in the vicinity of the sun. It was moving at 60 kilometers per second outside the solar system. So to go to the site of the meteor, we needed to know where it exploded. And the Department of Defense gave an error box of about 10 kilometers in size, but we were able to narrow down the meteor path based on the sound that was recorded from the explosion by a seismometer on Manus Island in Papua New Guinea. And from the delay between the sound wave relative to the light, we could tell how far the explosion was because the speed of sound is known. And it's just like the time delay that you notice between a thunder and a lightning. So we were able to pin down the path of the meteor to within a kilometer or so based on the distance from the seismometer. And that's what you see as the red strip on the right-hand side. So then we rented a ship called the Silver Star, and let me show you a few images from that trip with a song that mentions Silver Star. So just to explain the context, we were looking for the molten droplets from the surface of the object when it was exposed to the immense heat from the fireball that it generated. And the explosion released a few percent of the Hiroshima atomic bomb energy into about 500 kilograms of material. So there were droplets that fell on the ocean floor, and we were trying to find them. And the idea was to design a sled with magnets on both sides and drag it over the ocean floor and collect magnetic particles left over from this meteor. And this expedition, the cost of it was estimated at $1.5 million. As soon as I announced that we have to do this expedition, I had a Zoom call with the funder that provided these funds. And here we are on the deck of Silver Star. And what you see behind us is the frame that was used to connect the sled that we built to the ship. This cable that connected the sled to the ship was about 5 kilometers in length. The ocean depth was was roughly 2 kilometers at that location. So we were looking for millimeter-sized particles, the size of a grain of sand, at a depth of 2 kilometers across a region 10 kilometers in length. Sounds like an impossible mission. And here you see the team that came with me, 28 people, some of the best professionals, engineers, navigators for ocean expeditions in the world. And here are some photos from the ship. You can see in the middle and the right-hand side, the sled being raised out of the ocean and put on the deck, and then we would scrape the magnets on the two sides of the sled for any magnetic particles, most of which were volcanic ash, black powder, that we had to separate away from anything else. What you see at the bottom left and middle is me jogging at sunrise. That's a routine that I do on land, and I kept it also on the ship. And we had a filming crew on the ship, one that I selected out of 50 filmmakers and producers who wanted to be there. And one day they came to me and said they want to film me jogging. They asked me to jog 3 times longer than I usually do, it was about 15 kilometers. Then the director asked me, Avi, it looks like you're running. Are you running away from something or towards something? And I said, both. I'm running away from some of my colleagues in academia who have very strong opinions without seeking evidence. And I'm running towards a higher intelligence in interstellar space. So we scraped the magnets on the sled. You can see it at the top here, and used also a vacuum cleaner to collect those magnetic particles. And then we would dry them up, separate the volcanic ash, and put whatever is left, the bigger particles, under a microscope. So this is a new frontier in astronomy. In the past, astronomers used telescopes to find what lies outside the solar system. Here, we use microscopes, not telescopes. And let me show you how the sled collected magnetic particles from the ocean floor. And this is a video from a camera that was attached to the sled. And it's just like mowing the lawn, except that there is no grass at the bottom of the ocean, 2 kilometers deep. It's basically mud or muck. And we collected mostly volcanic ash, as I mentioned, but gladly, that was not everything that we collected. And in the first day, we had an issue of keeping the sled on the ocean floor because the cable would lift it up and it would be kiting above the ocean floor. And then after the first day, the engineers figured a way of maintaining the sled on the ocean floor by following the currents in the ocean. And here you can see that we took a rock for the ride on the ocean floor at some point. So after 6 days, we didn't find anything other than volcanic ash. And, you know, we went 26 times altogether back and forth across this region for 2 weeks. And between June 14 and 28 of 2023, this year. But on the 7th day, we started filtering out the tiny particles of the volcanic ash, and we started looking through a microscope at whatever remains, and we found the first spheral, the first molten droplet from a meteor. And I hugged the person who found it first because I was thrilled that here we are finding what we were looking for. The day before, I wrote a diary report saying, where are the spherals? I was quite unhappy about the fact that we haven't found it for 6 days. But then after we found the first one, I realized, well, there will be many more, because when I find an ant in the kitchen, I get alarmed. I know that there are many more ants out there. And indeed, we found 50 spherules during the expeditions, the 2 weeks that we were on the ocean. And then you can see here how these spherules look like. They are very distinct, different from the background sand, right where the white arrow is pointing. And we used tweezers to pick them up. And here are some images through the microscope of how these spherules look like. And when my daughter saw one of them, she said, Dad, can I have one of them on a necklace to wear? And I said, well, these are smaller than a millimeter. It's impossible to thread them. And we put them in vials. These are the babies that we delivered, just like the delivery room. The delivery room here is this basket, the white basket. And we then, just before we came back, I shipped those vials in a black suitcase that you see here using FedEx. And it arrived to my home a few days later after I arrived. And I realized that a few days of a delay are not too much, given that it took this material billions of years to arrive to the solar system. I didn't want to risk the material by leaving it in my suitcase, because it could have been lost in customs. And on the left, you can see us on a rainy night looking through the magnets, trying to see if there is more material that we may have missed. The person in the black raincoat is the funder, Charles Hoskinson. And then I brought the materials to the laboratory of my colleague at Harvard, Stein Jacobson, that you see here on the right. He's a world-renowned geochemist, and he has a mass spectrometer that could analyze the composition of these spherules. And on the other side, you see my summer intern, Sophie Bergstrom, and she found more than 600 additional spherules. So altogether, we have 700 of them right now that we are analyzing. And here are photos of some of the spherules that she found. And then my postdoc, Laura Domini, made a map of the yield of spherules. What you see on the left is a zoomed out map where you can see also the control regions far away from the meteor site, which is shown in orange. And near the meteor path, we found a high yield of spherules relative to the mass that was retrieved from the ocean floor. So interestingly, these yellow regions that you can see in the zoomed in version in the middle of this slide, these yellow regions that have a yield that is about twice as large as the background, they are close to the meteor path. So we were in the right place because we see a concentration of spherules around the meteor path. These were the excess spherules. They were found only in some specific runs, like 13, 14, 4. And interestingly, the spherules that we found in these runs include a very unique type that I will talk about in a minute. But let me show you some electron microscope images from the first day after we came back. We stopped at the University of California at Berkeley, and we used an electron scanning microscope to take images of some spherules. And what we found is that inside of them, there are spheres. So you find spheres inside spheres, which is sort of like Russian dolls. And the idea is that the small spheres solidified first, and then they were engulfed with liquid iron that glued them together to make the bigger spheres. So you can see them sitting on a dendritic background. And here is an image of a spheroid that looks like a soccer ball. And here is an even more interesting one that looks like a merger of 3 spheres that didn't have a chance to come together and make a spherical merger because they solidified before surface tension made this droplet spherical. And this one was one of the biggest spheroids that we found, bigger than 1 millimeter. So we decided to study it because it was in one of those yellow regions near the meteor path where the yield of spheroids was large. And first thing we realized is that it's not from this Earth. It came from outside of Earth because isotopes of iron were very different than those on Earth, and also those on Mars or the Moon. So clearly, this spheroid came from outside the objects that we know about in the solar system. But more remarkably, we plotted the composition of this spheroid after using the mass spectrometer. And what you see here on the horizontal axis are the elements in the periodic table, starting from lithium on the left and going all the way to uranium on the right side. And the abundance of various elements is normalized to the standard solar composition. So in other words, the materials that made the solar system. So that's a value of 1 on this plot. This line, horizontal line at 1, represents the standard composition of solar system materials. And what we found in this spheroid is that the abundance of elements like beryllium, lanthanum, and uranium is enhanced by a factor of hundreds. For beryllium, it's 300. For lanthanum, it's about 500. For uranium, it's higher than 600 relative to the standard solar abundances. And this clearly indicated that this spheroid came from an object that doesn't belong to the solar system. And here are 5 spheroids. All of them were found in the yellow regions where there was an excess of spheroids near the meteor path. And all of them show this composition pattern that we label as Belau for beryllium, lanthanum, uranium. And here we plot it as a function of the volatility of elements. So elements on the right side can evaporate very easily during an airburst, during an explosion in the air. And indeed, we find that elements on the right side are missing. So that shows that these spheroids came from an airburst, from an explosion in the atmosphere. And they have abundances that are hundreds of times larger than the standard solar composition for other elements. So the question is, where did this abundance pattern come from? And one possibility is that the object, this meteor, came from a planet that was a magma ocean where the rock was molten. And actually the Earth started that way because it formed out of the collision of heavy objects with the proto-Earth. And one of these collisions generated the Moon, which was also a magma ocean. And Mars also started as a magma ocean. But the composition of rocks on the Earth, the Moon, or Mars does not resemble the abundance pattern that we find. So it must be a planet that could have been a magma ocean near another star. And that is a natural origin. And the question is, where such a planet, a magma ocean planet, could originate from, and how would it produce objects that are moving so fast like this meteor? And by the way, this is the natural origin for such an object, Of course, there is also the possibility of a technological origin, where uranium is enhanced because it's used as fuel in fission reactors, or where lanthanum is enhanced because it's a substrate for semiconductors. But let's discuss first the natural origin. And in a paper that I posted this week, actually, I found a place where such meteors can be produced. And it's next to the most common type of stars. These are dwarf stars that have 1/10 of the mass of the sun. Turns out that if you take the Earth is denser than the sun. And so if you bring the Earth close to the sun, the gravity, the tidal force from the sun will not destroy the Earth. And the Earth would, only if the Earth gets into the sun, it will eventually end up destroyed by the heat from the sun. But gravity alone cannot destroy the Earth by the sun. However, if you consider the most common type of stars that are much less massive than the sun, they can destroy the Earth, because it turns out that a star with 10% of the mass of the sun is roughly 10% of the size of the sun. And so its density is 100 times that of the sun. And that is bigger than the density of rock on Earth. And so if the Earth were to come close to a dwarf star, then it will get destroyed. It will become spaghettified, just like a stream of rocks out of the planet. And here you can see a simulation of that, of what happens to a planet like the Earth that comes close to a dwarf star. It gets torn apart. We all know about what the moon does to the oceans on Earth as a result of tidal forces. We see the ocean rising and receding depending on the distance from the moon. But in the case of a dwarf star, it could actually destroy the entire Earth and make a stream of rocks out of that. And in the process of doing so, the rock on the planet will also get molten when it comes close to the star. Now, how do you get a planet like the Earth so close to a star? Well, it could get kicked into that position as a result of a companion to the star, either a Jupiter-like planet or another star. And here is what you get. You end up dispersing the Earth rocks into a stream of gas and a stream of rocks. And then what is the characteristic speed of those rocks that get ejected into interstellar space? Turns out to be very close to the speed that was observed for the first interstellar meteor, of the order of 60 kilometers per second. And this result is quite intriguing because, you know, it's just putting the numbers that are typical for dwarf stars and getting a result that is quite surprising, that you end up with rocks in interstellar space moving at 60 kilometers per second, very similar to what we observed for this interstellar meteor. And so the other question to ask is, are there enough rocks? And it turns out that if you imagine this happening to half of the rocks near a star, a dwarf star, then you end up with a collision every decade of rocks similar to this meteor, 500 kilograms in mass, every decade colliding with Earth from interstellar space. So that's another interesting result. And of course, there is also the possibility that we might have seen a technological object, and to find out, what we hope to do is search for bigger pieces. Now, this interstellar expedition was risky. There were many potential failure points. For example, I could have had no money to fund the expedition. Maybe engineers and navigators would not join me on this mission. and we could have not built the machinery necessary to accomplish our task. Also, the sled may have not been on the ocean floor. As I mentioned, the cable was pulling it up. And then even if it were on the ocean floor, we might have not found enough spherules from this first interstellar meteor on the ocean floor, because perhaps it didn't produce enough of them for us to find them. And then even if we were to collect them, we could have missed them among the background volcanic ash. And finally, when I came to my colleague Stein Jacobson and said, can we get your help? He could have told me that he has other projects and he cannot dedicate his research team to this project. And then we would never know about this Belau abundance pattern. So altogether, to me, the message from this is that it's worth taking risks in science, because if you are an optimist, sometimes life is a self-fulfilling prophecy. It gets better than you imagine. So the next expedition is aiming to find bigger pieces so that we can answer the question of whether this meteor was natural or technological in origin. And we hope to do it within the next 9 months. Now we know where to go because we have those spherules that we mapped that have an unusual composition. So we know exactly where to go. So that's all for what I wanted to describe. I'll be glad to take questions. So let me stop sharing the screen, and please feel free to ask me anything.
Okay, Rodrigo, just a moment, because we need to know if there is some question. We can translate. Nosotros podemos traducir las preguntas que tengan. Así que si las pueden hacer, pueden levantar la mano o a través de la plataforma. Mientras tanto, si algunos se entusiasman. Okay, please.
Dr. Lev, my question is in the boundaries of your presentation, actually. So I could see that you have or you are planning to have several more stations in United States territory. Have you thinking in having something in the southern hemisphere, because we are open?
Yeah, in principle, that is possible. We need a funder, someone that would be interested. And in principle, we can name an observatory after the person who provides the funds. And it's the funding is at the level of about $500,000 per observatory. It's not a lot of money compared to other astronomical observatories. And we know exactly the type of instruments and how to organize the data collection. And we are using artificial intelligence to analyze the data. So we have the recipe of making such an observatory. I should mention that the Galileo project is the first and only scientific project aiming to collect data on unidentified anomalous phenomena. There was never a project like that working, and a lot of people are intrigued by amateur footage or blurry images or whatever the government is willing to release, but that's not scientific quality data. So we are happy to partner with a funder that is interested perhaps in putting such an observatory in the south. And all that is needed is for that funder to contact me. And I should mention, I mean, there might be issues with export of some instruments, but in principle, all of the devices that we use are off the shelf, and they can be purchased at the country that we are collaborating with.
Okay, thank you very much. Just for the people that that is listening to us, I understand that this could be done in the terms of an agreement. So if
Right.
there's a university or something like that,
Right.
they can use information, we can interchange.
Yeah. So
exchange
I am obviously at
research.
Harvard University, and we do have, for example, in Chile, we have the Magellan telescope that we are currently operating in collaboration with other institutions. So definitely this can be regarded as a scientific collaborative project. And the Galileo project is housed at Harvard University. So definitely we can partner with, as long as there are funds to establish a new observatory.
Yeah, I understand. And so are you connected with our many observatories we have in Chile? I mean, European,
Yes.
Southern, and
Yes.
observatory.
Yeah,
Yes.
and as I mentioned at the beginning, I did visit Chile. There are many facilities there, and they're doing state-of-the-art astronomy in many different contexts, from the cosmic microwave background all the way to distant galaxies and nearby, star-forming regions and so forth. So there are many different instruments being used, and Chile represents the highest concentration of astronomical data output that I know of in a variety of frontiers. So adding objects near Earth would just be fantastic, because you have to understand that existing astronomical facilities are focused on a small region of the sky usually, and the telescopes are trained at looking at very distant sources. Whereas here we are talking about monitoring the entire sky at all times for objects that may fly overhead. And that requires a very different observing strategy, different instruments. And it took us 2 years to develop the concept, to design such an observatory from scratch, because no such observatory existed before.
Yes, well, just I remember that we have many researchers in Chile working with big data concerning astronomy, and
Yeah.
we're starting. I would say we're starting to have some projects concerning space objects awareness. So I think in the next future we could have something to help or to participate in Galileo project. Thank you.
That would be wonderful. And as I mentioned, a very important component that we are working on is machine learning, artificial intelligence, so that we can automate the data analysis. There is just no way that people will be able to go through the entire data. It has to be automated through computers.
Yes, of course.
Rodrigo, I have some questions. There is in the chat. How is the relation today with your colleges? Because you were criticized before because of your, let's say, you were pushing to find extraterrestrial material. How it is now? Because you mentioned during your conference that some were a little bit, let's say, reacting against you. So they didn't want to follow you. So how is the situation by now?
Well, it's really a problem about innovation in science more broadly, because what I can give you the example in my case, that when this meteor was identified, then people said we don't believe the US government data. And then there was this letter from the US Space Command, and that allowed our paper to be published. But still, when I decided to go on the expedition, then some people would say, why would you do that? You will not find anything. And then I said to them, look, I'm not asking you to do anything. I'm doing the heavy lifting. You just express your opinion. Let's see if we find something. And then we went there and collected materials. So on the way back, there was a paper published in the Astrophysical Journal by two experts on meteors saying, yeah, we insist that the US government data must be wrong. They got the measurement of the speed, they're wrong by a factor of 3. These were slower. This was a slower object that was probably a stone, because only if we make the speed measurement lower by a factor of 3, we can fit the data. And they basically said the data is wrong because it doesn't fit our model for solar system stones. And I call that the stone age of science, where everything in the sky must be stones. And if it doesn't agree with your model, the data must be wrong. You know, that is a very arrogant proposition, because the US Space Command is responsible for identifying ballistic missiles shot by North Korea, and they are supposed to alert the US president. They have a budget bigger than NASA. And so for an astronomer to say they don't know what they're talking about, even though they had this letter to NASA, and moreover, you know, this object is nothing but a stone. When I was bringing back materials that, you know, were mostly iron, you know, and clearly not a stone, you know, that is very arrogant and very inappropriate in science, because you should be modest. You should let the data speak for itself. And all I did was follow the scientific method. But they had a problem with that, because they had an opinion, and they didn't want those people. It's just a few people who were working on asteroids and meteors for decades and didn't want this object to be the first interstellar meteor. They have an issue with that. But my point is that we should follow the scientific method. And the way, you know, I don't want to get into mud wrestling because it will get me dirty. They expressed very negative opinions to reporters, but these are superficial. And, you know, you can find it. There was a New York Times magazine profile about me, you know, the only one about a scientist in recent decades. And I'm, you know, it's quite understandable that some people are jealous that there is attention to the research, but that's not my fault. You know, the fact that the public cares about it is really a testimony that to the fact that this subject is important to society. Okay, so I should not be penalized for the fact that other people care about it. And we should just follow the evidence and see what, and it was a lot of work to collect the materials, you know, and then analyze them for months at Harvard. But all I received from those individuals was negativity. And the way I approach it is just like in the metaphor of an eagle. You know, an eagle very often has a crow pecking on its neck. And what the eagle does, it doesn't fight with the crow, it just rises to greater heights where the oxygen level is lower and the crow just drops off. And my greatest heights is doing science as it should be done, by writing the best scientific papers that I can. And my hope is that those crows that are pecking on my neck will drop off. Now, they are very stubborn, these crows, because, you know, one way to think about negativity in academia is that people enjoy doing that because they want to step on any flower that rises above the grass level, you know, because they prefer, you know, it hurts their ego if something new comes along. And I see that as a dangerous trend because it discourages young scientists from innovating. Only if you follow the beaten path that is endorsed by, quote unquote, the adults in the room, only then you get you know, people to cheer you up. And that's very bad because innovation is suppressed this way and you can't make discoveries. I'm willing to accept the heat because I'm a tenured professor. I was chair of the astronomy department for almost a decade at Harvard University, chair of the board on physics and astronomy of the National Academies. I know how science should be done. And by the way, another brand of people that you see are bloggers or people that call themselves astrophysicists. I will not mention names, but some of them are popularized science. And you know, these are just like commentators that look at a soccer match and they tell the players how to pass the ball. And I say, how dare you? Like, you are not practicing what you preach for. You know, I'm a scientist. I publish papers. I write papers every month. I write a few of them. and I'm doing the scientific work, and those people did not write a single scientific paper over the past decade. So, and they still express very strong opinions, and reporters listen to them. And so this all is quite sad to see that if you want to pursue science the way it should be done on a subject that, you know, explores the unknown, why would there be so much resistance just because the public cares about it? You know, if you look at we don't know what most of the matter in the universe is. We call it dark matter. And of course, we have a lot of possibilities. And, you know, experimentalists invest billions of dollars in searching for specific types of dark matter. But nobody has an issue with that, even though we haven't found for 50 years through these experiments, we haven't found the nature of dark matter. We are searching hypothetical ideas. Why does nobody have a problem with that? Because the public doesn't care much whether the dark matter is an axion or a weakly interacting massive particle or small black holes. You know, the public, it doesn't affect the lives of people. But when I do my research and people care about it, that makes some quote unquote experts jealous. And I just think it's inappropriate, because I'm not doing anything more speculative than, you know, the mainstream of fundamental physics, theoretical physics, that works on extra dimensions. We have no clue whether extra dimensions exist. They work on the multiverse. We have no idea whether the multiverse. There are things that are far more speculative than what I'm doing. I'm just attending to anomalous objects in the sky. That's all I'm doing. So I'm not speculating. I'm saying here are objects that look different than we are used to. They came from outside the solar system. Let's study them. And that makes me controversial for studying objects that we know about and getting more data when people are talking about, you know, the multiverse where we have no clue whether it exists. I mean, this is crazy to me that you have this response to the scientific method. And I have very strong opinions about that, because I think it hurts innovation in science more broadly. And, you know, if you say, well, I'm not a SETI scientist, I don't need to argue about this subject. Okay, and then you say, I'm not a meteor scientist, I don't need to argue about this. Okay, but then eventually they will come after you if you try to do something different, irrespective of what you do, if it deviates from the mainstream, and then you will have nobody to protect you. So my point is, it's worth fighting this fight, because, you know, this is the way. I mean, science is like a detective story. We don't know in advance what we will discover, and we should be guided by evidence. So frankly, it's not about getting likes. And we knew that from the days of Galileo. He was put in house arrest. Today, he would have been canceled on social media.
Yeah. Okay. How about let's say, some engagement with the European community? Can you get some, let's say, help from them, or they can join you in this effort?
Yeah, we do have members of the Galileo project that come from Europe. By the way, it's an international project. There is no reason for us to avoid any particular. I mean, any knowledge about what lies outside the solar system should be shared by all humans. That's why I think the US government, for example, should not, if they have any information, any materials, they should make it public. I don't know if they have, but if they do, it should not be a matter of national security, because any object that came to visit us started the journey before humans came to exist on Earth. It didn't have us in mind, and therefore, you know, it's like any other study of the universe at large. You know, that's something we want to share with all humans, so that we know whether we have a neighbor. That will have huge implications for our future. You know, Steven Weinberg, the Nobel laureate in physics, argued at the end of his book, The First 3 Minutes, he said, the more we understand the universe, the more pointless it looks. And my point is that it looks pointless to cosmologists because they focus on lifeless entities like elementary particles, radiation, stars, dark matter, and so forth. But we know from our personal life that when we find a partner, it gives a meaning to our existence. So if we find another civilization out there, it will make the universe not so pointless. It will give us a meaning, and we will not feel lonely the way we do right now.
Oh yeah, absolutely. Rodrigo?
Thank you, Eduardo. I only have a comment. It will be always easier to research on things that we already know. So that's the problem. And
that's true.
And otherwise, yeah, these people is encouraging. I mean, stopping the young people on thinking with curiosity.
Yes.
Okay.
Exactly. And exactly. And the way I define myself is like a curious farm boy, because I was born on a farm and I'm just driven by my curiosity.
Yeah, that's right. And even today, when all our satellites and astronomical observatories are showing that the universe is full of organic particles that can be arrive in a good environment and produce life. So
yeah,
so
I think it's arrogant. It's arrogant on our side to believe that we are unique and special. And if you just look at the news every day, it's clear that we are not the pinnacle of creation. There could be something better than us out there, because we engage in wars. You know, there are 2 of them happening right now in the world. And what is a war? You know, it's just a waste of resources trying to kill other people. And nothing good comes out of that. Nothing good. And if we were more intelligent, instead of allocating $2 trillion a year on military budgets, we could explore space. And I calculated that if we were to spend $2 trillion every year worldwide on sending CubeSats, we could send billions of them within this century that would aim at all the stars in the Milky Way galaxy, just within 1 century. And it's only a question of priorities. And I think we have our priorities wrong. And perhaps one way to fix that is if we find a letter in our mailbox that gives us a wake-up call.
Yeah, that's true. And okay, so thank you very much for your research and the job you are doing. So we hope that will be that will be more credible for these people in the future, because it seems that from everywhere all the facts are arriving through logical thinkers. We're not the only ones in this huge and commensurable huge universe. So
yeah, and my hope is we will recognize that we are all in the same boat, sailing through space, and we should work together as equal members of the human species. And I really believe that it will bring us to a better place once we recognize that we are not alone. So let's hope that we will find it during our lifetime.
Yeah, thank you.
Yeah. Okay, thanks so much. Only something, we have a university that is building CubeSat. Can they be engaged with your project? There is some question.
Potentially, yeah. It depends specifically what they're doing, but they can reach out to me and I'll be glad to discuss it.
I will tell them. And the last question, because it's taking long for you, about the dwarf stars. Some is worried about, of course, you mentioned that it can, let's say, take the years and it will be destroyed. How far from us is the closest one?
Oh, it's about 4 light years. That's Proxima Centauri. And it's not heading in our direction. And the chance of a dwarf star close to us is extremely small. So don't worry. I mean, unless you are on a planet that was born close to a dwarf star, bound to it, there is no risk by those passing stars. So you can sleep well at night. I think the biggest risk is actually from what we are doing to our planet, from humans.
Yes.
more than
Yes.
any astrophysical object. So that's what we
Totally
need to
agree.
work on. Yeah.
Totally agree with you. Well, thanks, Professor Lev. Indeed, it has been a very fruitful journey for us. And we have a lot of things and a lot of information to eat, because it's a very broad and a very heavy subject. So we really appreciate your time, your generosity with us. And I hope it won't be the last time. Yeah, because really we love this issue, this theme. It is so important. And what you mentioned about what's happening in the world, absolutely agree with you. We should be doing something different. Okay.
Thank you so much. And I'm very proud of the fact that half of my DNA is Spanish in origin, by the way. So.
Okay. Thanks so much, Professor. And a big hug. And be okay.
Thank you.
And your
Bye-bye.
family. Okay.
Thank
Bye-bye.
you. Bye-bye.
Bye-bye. Rodrigo, ¿esa es la música?
Te comento ahora que tengo mi micrófono.
Ya.
Esta música es la música que hace Flanger. Tenemos otro video que vamos a poner en el futuro próximo, donde se comenta la forma en que se toman las frecuencias. ¿Puedes bajar el volumen un poquito, Constanza?
Pero el tiempo para al ver tu cara en el radio.
Te comentaba, Eduardo, que tenemos un video de un seminario en que se muestra la forma en que se sonoriza estas canciones que hace el cantante Joaquín Macaya, de nombre artístico Flanger, que tiene ya varias presentaciones en Chile y se está haciendo famoso con esto de tomar las frecuencias que se reciben en los observatorios radioastronómicos. Y toma esas frecuencias y con ellas se fabrica una secuencia musical, digamos. ¿Ya? Y él está creciendo de a poquito. Hace tiempo él es integrante de Achide y lo hemos estado apoyando, digamos, con su música, digamos, considerando que Achide integra no solo la parte científica, sino que todos los ámbitos del desarrollo espacial.
Claro, exacto.
Así que hay varias de estas yo creo que podemos escuchar en el futuro próximo, mientras en intermedio o un poco antes o después de nuestra presentación. Ahora, esta está quedando grabado al final de la presentación, por lo que me decía Constanza, así que vamos a tener de a poco más noticias acerca de esto, ¿ya?
Ya, perfecto. Oye, interesante es para verla varias veces la presentación, porque la verdad que hay conceptos, hay tanta física aplicada que es bastante complejo. Oye, y muy buena la pregunta de Sergio, porque lo dejó, pero ahí con dando explicaciones y contando la verdad. Lo que pasa es que es tremendamente cierto lo que ha tenido que enfrentar él. Así que era bien interesante saber cómo era o cómo es la situación con quienes hace algunos años atrás, sobre todo, estaban en contra de él en forma muy, voy a decir, despiadada, y obviamente para él dolorosa también, porque efectivamente lo que un científico busca es buscar evidencia y no tiene por qué haber ese celo extremo para tratar de bajar al otro, es decir, como aquí diríamos, el chaqueteo. Así es que, ¿cómo estuvo la comprensión, Sergio? Porque en inglés bien.
Claro. No es difícil seguirlo, digamos, y el apoyo de las imágenes, todo lo más, te da una noción bien clara de lo que está conversando, digamos.
Sí. Bueno, brillante nomás, ¿qué más podemos decir? Uno se siente una partícula, y la pregunta es cómo poder colaborar con eso. Por eso que le hacía una pregunta también de que estos muchachos de la Universidad de Chile están trabajando con los CubeSat y a lo mejor ahí podríamos lograr con ellos que hicieran contacto y generar ahí una energía con ellos, porque ellos están investigando y podría darse justamente una ventana para que trabajaran en conjunto con alguna dirección, porque ellos están aprendiendo, pero también lo que pueden lograr es instalar sensores de mucha mejor calidad y poder también entregar alguna evidencia. Así es que...
Exactamente. Oye, y se abre también la oportunidad para, bueno, como decía él, necesita gente que provea fondos, ¿no es cierto? Pero se abre la
Exacto.
oportunidad para que nuestros proyectos en Chile también se puedan abocar a este sistema. Así que bueno, yo creo que quienes nos están escuchando, ¿no es cierto?, ya quedan por lo menos con el bichito de que esto también existe, el estudio de los cuerpos interestelares, y hay que contactarse con Abraham Led para ver si podemos hacer algo más en profundidad en investigación en esa área. Eso sería todo por mi parte, Eduardo. Sergio, muchas gracias.
Ya.
Listo, gracias.
Gracias,
Que estén muy bien,
Rodrigo.
gracias a ustedes.
Gracias, Sergio, a Rolando, a todos quienes están conectados y a quienes están en el streaming. Y aquí hay un polo de desarrollo, así que tenemos una oportunidad y ojalá que algunos lo tomen. Nosotros solamente aprovechamos la oportunidad y darle la plataforma y generar los vínculos, el famoso networking. Así que muchas gracias a todos y nos vemos a la próxima ocasión, la próxima semana.
Nos
Ya.
vemos.
Okay.
Adiós.
Thank you.
Hasta pronto.
Chao,
Chao.
buenas tardes.
Chao, buenas tardes.
Pienso solo en irte a ver. Con el corazón destrozado. Y nunca me olvidaré que jamás se iba a poder. Estaba perdida, estaba cansada. Sentía ese sonido como una espada. Busqué en toda la tierra y no encontré nada. Por eso me fui a la estrella y en la inmensidad del espacio. Es mejor si me voy despacio. No hay ningún camino mejor que el destino. Y aquí mismo me hice un palacio. Vamos lejos. Con el beat va mi corazón al mismo ritmo que esta canción. Vamos lejos. Con el beat va mi corazón. Yo soy quien soy, no pido perdón.
Apaguen motores, los propulsores, apaguen todas las comunicaciones. No son necesarias todas las misiones. De aquí se ven todas las constelaciones. Dibujen recuerdos que tengo dentro. Llueve meteorito y estoy contento. Todo eso que han dado en lo que me pierdo. Encuentro la llave, me pecho.
Es tan necesario conversarse a diario. No estoy modo avión, estoy modo halcón milenario. Se acaba el combustible y se rompe el escenario. Te busco hace años y por las noches te callo. Vamos lejos.
Con el beat va mi corazón al mismo ritmo que esta canción.
Vamos lejos.
Con el beat va mi corazón. Yo soy quien soy, no pido perdón. No, 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 no. Vamos
Toda una vida mirando al sol, buscándome allá en el espacio exterior.
y entre el ruido,
La distracción, en el silencio soy mi propia inspiración.